Now I would like to do LC oscillators. So now we would like to do LC oscillator, and so we have learned that a capacitor stores electrical energy, and we also learned that inductor stores magnetic energy. So these two components, electrical components, one would stores electrical energy, another would stores magnetic energy. So this is how we are going to discuss about oscillator, right? So this is what I have. So in a very simple word, we say that capacitor, and then I will discuss how oscillation takes place. Capacitor stores electrical energy, right? Electrical energies. Capacitor stores electrical energies. Capacitor stores electrical energy. How much electrical energy it stores? Very simple. This is Q square by C. This is the energy stored by capacitors, right? And what about inductor, right? What about inductors? So inductor stores, all right? Inductor stores magnetic energy, right? Magnetic energy. I would like to write here. This is electrical energy 1 by Q. This is the charge on the capacitors, and inductor stores the magnetic energies. This is equal to half Li square. I is the current, right, in inductors. This is the very important concept, right? And now this is how oscillation takes place. Oscillation means electrical energy stored by capacitor. Sometimes this energy is transformed to magnetic energies. So there is a transfer of energy taking between the capacitor and an inductor is taking place. As in case of mechanics, we talk about pendulums, right? We talk about mechanical energy, that is a kinetic energy and a potential energy. So kinetic energy change into a potential energy, and sometimes potential energy change into a. This is how transfer of mechanical energy taking place within a pendulum, right? So very similar to this in case of LC oscillators, the magnetic energy and electrical energy, they transfer each other. All right. So how I am going to start is at any instant of time t. This is Q is charge on a capacitor at any instant of time t, and I is current in an inductor at given time t. Right? This is at time t. At time t. Right? So how I am going to proceed that oscillation is that. So initially I said I charge capacitors. Initially capacitor, I charge capacitor. I'm going to charge capacitor, right? I'm going to charge capacitors, and so capacitor would be having let's say initially time is going to be t is 0. That is initially charge on a capacitor is going to be a maximum, right? Maximum charge on a capacitor is going to be maximum, right? And current in an inductor is going to be 0, right? Current in an inductor is going to be 0, right? So initially I am going to charge capacitor using some battery, right? So what I do is I'm going to connect. I'm going to disconnect the capacitor from a battery, and I'm going to connect inductors. Once I connect inductors, there will be a flow of current taking place in the inductors. All right. When a flow of current taking place in the inductors, what happens is that charge in a capacitor start decreasing. All right. So I would say that charge in a capacitor start decreasing with the increase with the increase in a current in the inductors, with the increase in the current in the inductors. This is how it goes, right? This is how, and also sometimes the capacitors, right? Charge in the capacitor is fully exhaust, and current in the inductor is going to become maximums. And then again, there will be flow of current in a, there will be a charging of capacitor taking place. Initially, discharging of capacitor taking place. Now, the charging of capacitor taking place, and a current in the inductor is going to decrease, and the charge in the capacitor start decreasing, and this is how it takes place. Alright, so just say, so at t is equal to 0, initially, Q is equal to Qm, I is equal to 0, right? So this is what we have at initially condition, right? So now at any instant of time t, right? At any instant of times, at any instant of time t, Q is a charge on a capacitors. Q is a charge on a capacitors. Charge on capacitors, and I is current in a inductor. So this is what we have. I is current in the inductors. And then at that instant of time t, I use the Kirchhoff's rules. I say that Q by C is the voltage on a capacitors minus L di by dt is equal to 0. This is what we have. Whatever charge it has is going to give whatever voltage, voltage on a capacitor decreasing, however voltage on a inductor start increasing. This is what we have. This is using Kirchhoff's rule. And one more very important is that and if Q decreases, alright, Q decreases, then I increases. Alright. Therefore, this is what we go. Therefore, I can be defined as minus dq by Q decreases. I would say right here, right? Q decreases, I increase. So this is how I'm going to write, and then di by dt can be di square by dt. I'm sorry, di by dt can be written as minus dq. This is second order differential equation, right? This is second order differential equations, right? So I substitute this. Minus L minus plus 0. All right, and then I'll write here dq dt square plus q by LC equal to 0. So this is a very important equation. This is very important. This equation is what this is. I say this is second order. This is the second order differential equations. And this equation represents simple harmonic motions. This equation represents simple harmonic motion. Here, what exactly mean by simple harmonic motion is that the charge, how charge decreases and how current decreases, how current increases, how charge increases, how charge decreases is very much simple harmonic in nature. I would like to explain this. So this equation is normally what we call as a second order differential equations, which represents a simple harmonic motion. So here, so simple harmonic motion, I mean how charge decreases and how charge increases, and how current decreases and how current increases is very much in a simple harmonic nature. So this is so the equations. So I would like to write down the solution for these equations. So solution of this equation, I can write this is Q is equal to Qm cos omega t plus phi. Phi is some phase, some angle, right? Phi is some phase angle, right? So I would like to find out how much is phi. I would like to find out how much is phi. So I would say naught. And having said that, LC, right? Having said that, 1 by LC is equal to omega naught square, right? 1 by LC is equal to omega naught square. Or else I can write this in this form, right? Q equal to 0, right? This is what we have. Having said that 1 by LC is equal to omega naught square. Alright. So now I say that at t is equal to 0, at initial t, Q is equal to Qm. Q is equal to Qm. Alright. Then Q is equal to Qm cos phi, which implies that phi must be 0, right? Phi must be 0. If phi is 0, then cos phi is equal to 1. Alright. So which implies that phi is 0. So now my final equations, the final solution would be, this is the final solution, right? This is the final solutions. Now I would like to find out, this is the instantaneous charge on a capacitors. Now how much would be an instantaneous charge in instantaneous current, right? So instantaneous current is going to be minus dq by dt, alright, minus Qm dq by dt cos omega naught t, and then I is equal to minus Qm omega naught minus sine omega naught t. Okay, so this is what I have. This is what I have. And I would like to write here. So how much is I? So I is equal to minus into minus is plus Qm omega naught sine omega naught t. And where In is going to be Qm omega naught. In is going to be Qm omega naught. This is what I have. So therefore, I is equal to Im sine omega naught t. So look at here. This is a very simple fact that Q is represented by a cos and the I is represented by a sine. So that means these two are inverse. These two are inverse. That means if a charge is decreasing and the current has to increase. So this tells the simple harmonic nature. This tells the simple harmonic nature, right? So this is one, and I say that and this tells that the charge decreases, current increases, and how it increases, how it decreases is simple harmonic nature. Why? Cos is the simple harmonic expressions, and sine is also a simple harmonic nature. Cos and sines are simple harmonic in nature. So this is what we have. And now I have energy, right? So electrical energy, which I represent this by Q square by C, right? So Q is oscillating, right? Q is oscillating. So this is the charge oscillating, and I write here QB. This is potential energy in terms of a magnetic field is what we have. All right. and this is at any instant of time t, right? So total energy is going to be, I would like to say total energy is going to be V E plus V P. So this is what we have. This is what we have. All right. And if electrical energy is maximums, if electrical energy is maximums, then this is equal to total potential energies, which implies magnetic energy is 0. Similarly, if magnetic energy is maximums, then which implies electrical energy is 0. So this is what we have. This is what we have in case of springs and a pendulum. If it is a potential energy, if a potential energy is maximum, it is equal to total energy, and then kinetic energy is 0. Vice versa, right? So this is what we have, and this is what I have here in this case. So I will give you this. We would like to discuss this in analogy with the spring that is done in class 11, right? Very much done in class 11. So this is how this is there in textbook. You can see it very carefully. So here I would like to explain. Here the entire energy is electrical energies. Why? Because current is going to be 0 in a inductor. So this is the maximum kinetic energy, maximum electrical energy, and magnetic energy is 0. Now next, at any instant of time t, it has some potential, some magnetic energy and some electrical energies. And if I add up both, this is going to be our total energies. Now here in this case, charge in a capacitor is going to be 0, and there will be only current. So therefore it is the maximum magnetic energy, and the total energy is equal to magnetic energy. So this is how oscillation takes place. Electrical energy, then both electrical and magnetic energy, then only magnetic energy, and then both magnetic and electrical energy, again electric. This is how oscillation takes place. This is how oscillation takes place. So this is potential energy, kinetic energy 0. It has both potential and kinetic energy, and it has potential 0, kinetic energy is maximums, both kinetic and potential energy, and kinetic energy is maximum. So this is what we have in case of pendulum, right, or spring pendulum, right? Now next, last part I would like to discuss is, this is what we have energy, right? You can see this, you have done this. This is done in class 11, right? Now last part of this chapter is transformer. Last part of this chapter is transformer, and very important topic also. Transformer is a device mainly used in the alternating currents, mainly used in the alternating voltage. The job of transformers, what is the application of transformer, right? The job of transformer is to change AC voltage, right? AC voltage from greater to smaller, right? From greater to smaller, right? Or smaller to greater, whatever, right? So it is used to convert, used to increase or decrease alternating voltage. So the job of transformer is to increase or decrease alternating voltage. So this is this can do only. And then why it is very essential is we have done in our power transmissions the minimum loss of power transmission. Minimum loss of power during a transmission is possible if the voltage is very high and current is very small. So this is how transformer help us to maintain a high voltage, very high voltage. So this is the application of transformer. And then what about the principle, right? The principle is the mutual inductance. Alright, principle is a mutual inductance. Why? Because you will be having a two coil. You will be having a two coil, right? Mutual inductance. And then a Faraday law of inductions. Faraday law of inductions. Faraday law of inductions. So this is the principle behind the working of transformer, right? Now, as far as construction is concerned, transformer consists of a two coil, right? Transformer consists of two coils, and one is what we call as a primary coil, another one is what we call as secondary coils. And you have two different constructions, right? Maybe one constructions you put one coil over another coil. This is the one example. You are going to put one coil over another coil. You are going to put one coil over another coil. This is one construction. Another construction is that you are going to wind. You are going to put the coils on a two separate limb. You are going to put coils on a two separate limb. So this is the construction. And then one more is that in case of a transformer, you are going to wind. You are going to put wire on a soft iron core. Soft iron core, right? And so that the wires, right, are insulated. They are insulated from one another, right? So wires, when you put wire like this, the wires are insulated from one another. The wires are insulated from one another, right? So this is one very easy. So I'm going to put wire, all right, over a soft iron core, all right, so that the wires are insulated from one another. This is a very important concept. So I'll be having a two either two limb or one particular coil or iron core, or which you are going to wind a wires. This is what we have. This is how we have iron core. This is what we have. So last class we talked about this. Why we put laminated steel core? Why we require laminated, right? In order to reduce eddy current. So one is called primary coil, another one is called secondary coils. Okay, now having this, now I just say a primary winding or primary coils. Primary coils, and then I have a secondary coils. I have secondary coils, and I say a primary coil is taken as an input source. This is the input. This is going to be an input, and secondary winding is going to be an output. All right. You are going to put a voltage. You are going to supply voltage at a primary coil. You are going to take out a voltage from secondary coil. So this is going to be an input. This is going to be our input terminal. This is going to be output terminal, right? And a primary coil will be having NP number of turns, and the secondary coil will be having NS number of turns. This is NS number of turns, right? This is what I say turn. This is what we have. And then, next, there will be a flux linkage as I talk about mutual inductance, right? So, what I would like to do here is, in case of ideal transformer, right? Whatever flux link, right? Whatever flux is there in a primary is linked to secondary coils. Whatever flux is there in a secondary coil is linked to primary coil. This is how we have done this in a mutual inductance, right? So the flux of the magnetic flux of a primary coil is totally linked to a secondary coil, and magnetic flux of a secondary coil is totally linked to a primary coil. This is how we have done it. So there is no loss of flux taking place. All right. So therefore, now look at here. Now, in case of alternating voltage, in case of alternating current, right? In case of alternating current, what we have is if a current in a primary coil is changing, right? If a current in a primary coil is changing, right? This is secondary coil, right? If a current in a primary coil is changing, then magnetic flux is also changing, right? And then what about the current induced in a, what about a voltage induced in a secondary coil is going to be this, right? Minus and this is what we have. And I would say that this is the rate of change of flux. This is the rate of change of flux. This is the rate of change of flux. This is the rate of change of flux linked to primary coil, linked to secondary coil, linked to secondary coils. Alright, linked to secondary coil. And each turn has this mean number of rate of change of flux, then the total rate of change of flux is going to be multiplied by ns. Similarly, there will be a rate of change of magnetic flux linked to primary coil itself. Similarly, there is a rate of change of magnetic flux linked to primary coil itself. This is what we call as a back EMF. This is what we call as a back EMF, right? NP is the number of turns in a primary coil. This is what we have, and this is what we call as a back EMF. This is what we call as a back EMF. Alright, having said that, look at here, having said that, I just say that one approximation that I'm going to do is that the resistance of a primary coil is going to be a very small. The resistance of a primary coil is going to be a very small. Alright, the resistance of a primary coil is going to be a very small, and the current in a primary coil is going to be a small. Therefore, I just say that this is going to be Vp. Alright, and EMF in a primary coil is going to be voltage in a primary coils provided resistance of primary coil is very small. Resistance of primary coil is very small. And then one more I would like to do is ES is equal to Vp. The EMF across a secondary coil is equal to voltage across a secondary coil. Voltage across a secondary coil. Alright. Fact that the secondary coil is connected to a very high resistance. Very high resistance. Alright. So why? Because the secondary coil is connected to a very high resistance. Very high resistance. Alright. Therefore, Vs is equal to ES. Alright. So having this, I will write that. Alright. Instead of EP, I'll just write Vp. Vp divided by Np minus d phi by dt, and Vs divided by Ns equal to minus d phi by dt, and I equate these two equations, and finally I get Vp divided by Np is equal to Vs divided by Ns. This is one equation. Alright, this is one equation. So this is how I relate. Voltage and number of turns. This is how I relate voltage and number of turns. So I just say that Vp divided by Vs is equal to Np divided by Ns. That means if I increase the number of turns, then voltage is going to increase. If I decrease the number of turns, voltage is going to decrease. This is one case. And then another one, taking a transformer as an ideal transformer, taking a transformer as an ideal transformer, taking transformer as an ideal transformers. So when I assume this thing, I assume that transformer is an ideal transformer. So we say that primary resistance and currents are small for ideal transformer. The same flux link both the primary and the secondary coils. These are the assumption for ideal transformer. And then secondary current, the secondary current is very small. Why? Because the secondary coil is connected to a very high resistance. And then one more I would like to add is the transformer is assumed to be 100% efficient. So there is no power loss. There is no power loss. Under these conditions, input power is equal to output power. Under this condition, input power is equal to output power. So what is that input power? Alright, VPIP is equal to VSIS. This is what we have. There is no power loss. Actually, there is a power loss, but since we assume it as ideal transformer, there is no power loss. So therefore, Vp divided by Vs is going to be Is divided by Ip. This is one more equation. This is one more equation I take. Alright. So finally what I am going to take is taking this Vp divided by Vs, Vp divided by Vs, and then Np divided by Ns, and then Is divided by Ip. So this is the transformer equation. This is what we term as a transformer equation, and this equation tells us how current is related to number of turns and how current is related to a voltage. So this equation tells that if I increase the voltage and current is going to decrease. Alright. If I increase the current, voltage is going to decrease. So this is what we talk about transformer, right? So having this, now we talk about step up transformer and a step down transformer. We'll discuss what is step up transformer and step down transformer. So if I just say step down, first I step up and then I say a step down. So in case of step up and S is more than NP. In case of step down, and S is less than NP. So in case of a step up transformers, voltage is going to increase. And in case of step down transformer, voltage is going to decrease. Step down, voltage is going to step down. So in fact, there are number of turns in a secondary coil has to be more than a primary coil. Number of a secondary coil has to be less in case of a step down. And then voltage is going to be more and voltage is going to be less in the secondary, and the current is going to be less and the current is going to be more. This is what we have in case of step up and step down. Very simple, alright. So now last I would like to do a very simple discussion on the power losses occur due to a following reasons. So in case of now you won't find an ideal transformer, right? So therefore in normal transformer these problems normally arises. So flux leakage, that means the primary coil flux is not equal to secondary coil. The flux linkage is not equal, right? And there's a resistance in our winding wire, right? Because of which power loss take place. And there is a eddy current, right? The coil we will be having an eddy current because of which the power is going to lose. And the last is the hysteresis, right? So because of ED currents, because of ED currents, right? Because of the magnetic field, right? Because of magnetic field, there is a loss, right? Why? Because the core become magnetized, and then afterwards core become demagnetized, due to which there will be loss of some energy. All right. So you read this part in a textbook. So with this we come to an end of chapter number 7. Okay. Thank you.